All right. Hello, everyone. I'm Bernd, and this is for day 16 of Advent of Code. This puzzle was quite a challenging puzzle for me. It took me a while to figure it out, but let's have a look into it. So, day 16 was a graph puzzle. We are given a graph of valves, and each valve is connected to a few other valves by tunnels. Also, each valve has a flow rate, and the flow rate tells us if we open the corresponding valve, that's how much pressure will be released per minute. We want to go from one valve to another and open a few valves, and then we want to release as much pressure as possible in 30 minutes. Going through one tunnel takes us 1 minute, and opening one valve will also take us 1 minute. Let's have a look at the solution. So first we can look at the input, and we can notice that most valves will have a flow rate of 0. So there's no point opening those valves. And there's only a few valves with a positive flow rate. We'll consider those the active valves. And then to solve part 1, we of course need to read the file and split it into lines. And then we want to parse the lines. So we can use a trick and in each line find all the pairs of uppercase letters. This will give us the current valve as well as all the valves with tunnels from the current valve. And we can also get all the flow rates. And we keep track of the active valves. So valve is active if it's either the starting valve, AA, or if the flow rate is positive. We also, since it's a graph problem, we also want to get the shortest distance from a valve to all the other valves. So you can do this by iterating through all the valves. And at first, the distance from the valve to itself is 0. And then we go through a queue where it starts with the original valve. And then for each valve, we go through all the neighbors, all the valves that have tunnels to. If we already considered the valve and it's in the distance keys, we continue. Otherwise, the distance to this new valve from the original valves will be the distance to the previous one plus 1 because it takes us 1 to go through the tunnel. And then we append the new valve to the queue so we can always consider its neighbors. And since we always increase the distance by 1, the queue will always be ordered by distances. So this is why this works, and it also gives us the shortest distance for a particular valve. We can do this for all the valves. And then we only care about the active valves, so we can also only get the data for this. So we will present the active valves as indices, and we'll have a dictionary that maps the index to the name of the actual valve. And then we'll, for example, define these active distances as taking two indexes as inputs, and then it just gives us the shortest distance between the first valve as well as the index of the second valve, or the valve corresponding to the second index. Yes, we will solve the problems by considering states. So a state is all the important information that lets us know how much more pressure we can release at a particular position. So a state will have a current valve, so the position we're at. We'll have the remaining time, and we will keep track of which valves are already open. So you know that in order to know which valves we can open in the future. So yes, a state is given like this as a tuple of two integers and as well as a tuple of all these booleans that tells us whether a valve is already open or not. And we put all the data into a data class in order to pass it around more easily. So one is we have this dictionary of maximal pressure. So for each state, this will give us a maximum pressure we can release from this state. And we'll iteratively fill this dictionary. And this will then also give us the solution. And we also have the neighbors, which for each valve give us a dictionary. And each valve, it will tell us it will give us for each other valve or each index of the other valve, it will tell us the nearest the distance between those two valves. And we'll also have a dictionary where it tells us for each valve the flow rate of that valve. Yes, so in order to solve the problem, we again want to get data and set the data, and then the initial state will be given by this. So the current valve, the starting valve, is index 0. The remaining time will be equal to 30 minutes, the total time, and all valves will be closed. And then we want to call this function set maximal pressure, which will set the maximal pressure for the initial state by looking all the potential next states and setting the maximal pressure for them. And this is done by again looking at their next states and setting all the maximal pressure for them and so on. And then having set the maximal pressure for all the important states, we can just return the maximal pressure for the initial state, and this will be our solution. So to define this function, one thing we need to get the next moves for a particular state. So for a state, what we consider a move is going to another active from the current position, going to an active valve and opening this. This will be a move. Going to a active valve and not opening it, for example, does not make sense. So all the useful moves are going to an active valve and opening it. Okay, so what will be the new states or next states? So for that, we consider all the neighbors of the current valve. If the neighbor is already open, there's no point going there because we cannot release any extra pressure by doing that. So we continue. Otherwise, we'll look at the remaining time once we arrived at the new valve. This will be the remaining time we have now, minus the time it takes us to go. This will be the distance, and minus 1 because it takes us 1 minute to open the valve. Then we will consider the pressure we'll be able to release by opening that valve. So that will be the flow rate of the valve times the remaining time we have after opening the valve. We will also have to update the valves that are open. So that will be the same as what's been open for before for the previous state, but the new valve will also be open. And then we can use this to define the new state, which has the new valve, the new remaining time, and the new valves that are open, and add it to the next states. Okay, we can use that to set the maximal pressure for a particular state. So if the maximal pressure is already in the keys of this dictionary, or if the state is already in the keys of this dictionary, that means we've set the maximal pressure before. We don't need to do it again conveniently, so we can just return. Otherwise, we start with maximal pressure with 0, and then we go through all the potential next moves. So this will give us pressure released by the move as well as the next state. And then we will set the maximum pressure for the next state. So that will iteratively set the maximum pressure for more and more states. And after having done that, we know to get the maximal pressure of the new state will be in the dictionary. And then the total pressure released by doing this move will be the maximal pressure released from the next state as well as the pressure released by this move. And then the maximal pressure will update that if the total pressure, this move is good and releases a lot of pressure, will update the maximum pressure essentially. And then we have to obviously set the dictionary. We'll have to set the maximal pressure of the state as this maximal pressure we just computed. Yeah, so that will iteratively calculate the maximal pressure for all the states. And as I said, then that will allow us to just return the dictionary value at the initial state as a solution. We can do a little test, and with a bit of luck, that looks great. So it works on the test input. We can also run it on the original input. It also works out and quite quickly. So that is nice. For part 2, the problem becomes slightly harder. So there we don't have only one person going around and opening valves. We actually have 2 people. And they independently walk around and independently open valves. And then we want to know again what's the maximal pressure can be released by 2 people. So in this case, a state will be a bit bigger, has a bit more elements. So we have for the first person the time and the corresponding valve. And for the second person, we have as well the time that's left and the current valve. And then again, we keep track which valves are open. Again, we want to store all the data. And this time we want to have a different strategy of solving it. So for each state, we'll not consider exactly how much pressure we can release from that state, but we just calculate an upper bound, and then we'll keep improving these upper bounds. So that also requires us, or for that is useful to have an ordered list of next moves for each state. So that will tell us the state, essentially the first element there would be the state, the next state, but the next state that has the worst upper bound that corresponds to the worst upper bound of the current state. And we also need to keep track of the neighbors or pass around the neighbors and the flow rate. Getting the next move is a bit different than part 1 because now we have more 2 players. So, for state, we assume that the time 1 is always smaller or equal to time 2. That just reduces the number of states you need to consider. If the time 2 is 0, then that also means time 1 is 0 and there's no more moves to be made, so we return an empty list. Otherwise, we again go through all the neighbors of the so we will only consider we'll only allow the second player to do a move. So we'll go all through the neighbors of the valve where the second player is at. If it's already open, there's no point going to the valve, so we continue. Otherwise, we'll again calculate the remaining time as the remaining time before, the time it takes us to get to the valve, and the time it takes us to open the valve. If that's small, if that's 0 or less, there's no point going. And then we calculate the pressure we will release by going there. So it will be the new time that's left times the flow rate. We again set the new set of open valves, and then this time we have to distinguish if the new time is smaller than the time. We need to like add the new time in the new valve before at the first position, and otherwise we'll add it at the second position. And then we add this state to the next states, and we will need to consider one more state because we also only allow player 2 to make moves here. We also maybe player 2 doesn't want to do any moves anymore and let player 1 do a few more moves. So we have this retiring moves where we just set player 2 position and remaining time to 0 and let player 1 do a few more moves if that's an advantage. As I said, we want to keep an upper bound for states. So for that, we want to set a basic upper bound. So for that, we go through all the valves. If it's open, we don't care. Otherwise, we'll consider it for the upper bound. In particular, we will consider both players, how long it takes them to get there, as well as how much time they've left. And this will give us the remaining time that they have when they could be arriving at this particular state. We consider the better one of those two remaining times. And then this tells us how much potentially we could gain by going to the particular valve and opening it. So it'll be like, that's the pressure that could be released. And then we add this to the upper bound. So this upper bound will correspond to kind of at the same time going to all the remaining closed valves and opening them. So it's definitely an upper bound, could be loose. But yeah, it works as an upper bound. And then once we have an upper bound, we need to recursively improve them in order to at some point achieve like a tight upper bound that gives us the solution as well. So as I said, for each state, we'll have this ordered list of a queue of next states. If we have not set that yet, we need to set it. If there's no valid next moves, then the upper bound, then we can gain 0. We can release 0 more pressure for that state and we'll return. Otherwise, we look at this move corresponding to the highest upper bound. This will tell us the pressure released by doing this move as well as the next state. And so, because it's recursive, we want to improve the upper bound for this state. And when we do this, we keep track of this has changed. So this tells us whether the upper bound has improved by doing this recursive improvement. And we know that if there's no change anymore, then the upper bound corresponds to something we can achieve, and we'll turn that as a solution. But yeah, back to the algorithm. So we will so this move that corresponds to the first upper bound will improve this move, and then potentially this improves the upper bound of the state. So the upper bound corresponding to the move then will be the pressure released by the moves, as well as the new improved upper bound for the next state. And then we'll add this move back into the queue with this updated upper bound that it gives for the original state. And then we look at the first thing in the queue without removing it, and the priority will give us the new upper bound for the corresponding state. And then we just need to check if the new upper bound improved on the old upper bound. Then we set this has changed to true because some upper bound has changed. And we update the upper bound in the dictionary. So yeah, this gives us a way to improve the upper bound of a state based on all the next states. And if we do that long enough, hopefully we'll get to the optimal strategy. So something we needed in there was setting the ordered next move. So that will be the ordered next move will be a priority queue, and we add moves to it based on their upper bounds to the original state, which will be the pressure released by a particular move, as well as the upper bound to this new state. Okay, so this code allows us to solve the problem. So again, we want to, like in part 1, get the distances and the flow rates for the active valves. The initial state will be slightly different. So we have the first person is starting at position 0 and have 26 minutes left. And the second person will also start at position 0 and will have like 26 minutes in total left. And all the valves will be closed. And then we set the basic upper bound for this initial state. And then we recursively improve the upper bound for the initial state by again going through all the states corresponding to the first upper bounds and improving them. And we do this as long as improvement happens. And if we cannot improve the upper bound anymore, we know that this upper bound is tight and gives us the solution. So we can run a little test. And it looks good. Yes, so we also can run the code on the actual input. It takes us a bit to run, but about 13 seconds, I think, so nothing crazy. And yeah, then this also gives us the right solution. All right, so that was day 16, bit of a harder puzzle. I hope you still enjoyed it. Best of luck for the future, and see you around.